Bioconjugate Modeler is a module in MolCube apps that enables users to conjugate two components through a linker. In this video, we will demonstrate three use cases. The first and second cases focus on generating antibody-drug conjugates, or ADCs, using an antibody, a linker, and a payload. The third case demonstrates how to generate an antibody-RNA conjugate, or ARC, using an antibody, a linker, and RNA. To begin ADC modeling, the structure of component 1, which is the antibody, must first be prepared using the PDB Reader module. Please refer to the PDB Reader demo video for detailed instructions on how to generate this structure. Case 1. In Case 1, we will generate an ADC using predefined linkers and payloads. In Step 1, the user selects a previously generated PDB Reader project as Component 1. The list of available projects is automatically filtered based on the selected force field. The user can confirm the selection using the Select button or change it if needed. Once the selection is finalized, clicking Submit will move the workflow to Step 2. In Step 2, the user defines the conjugation site on Component 1. This is done by specifying the residue name, chain, and residue index, and then adding the selection. Multiple conjugation sites can be defined if needed, and all selected sites can be reviewed and modified in the selection panel. After confirming the selected sites, the workflow proceeds to the linker selection step. At this stage, the linker is selected from a database containing over 100 predefined linkers. These linkers are automatically filtered based on structural compatibility with the selected conjugation site. If desired, this filtering can be turned off or adjusted using additional filtering options. The user can preview linker structures, search by ID, name, SMILES, or MCS, and then apply the selected linker. The available conjugation sites on the linker are highlighted, and the user can choose the appropriate site before confirming the selection. Next, Component 2, which is the payload, is selected. Similar to the linker, a database of predefined payloads is available, along with filtering and preview options. If the selected payload does not have a predefined residue name, the user must assign one for the output structure. After selecting the payload and its conjugation site, the user confirms the selection to complete the component setup. Once all components are selected, the workflow provides a summary of the configuration. The user then selects the ligand force field and performs a structure check. This step allows verification of bond formation and conjugation sites in the final structure. For larger systems, parameter generation may take longer, and a fast option is automatically applied to improve performance. After confirming that the structure is correct, the user finalizes the configuration. Each finalized structure is stored as a conjugated set, and multiple sets can be created to model heterogeneous ADCs. After completing all selections, the user proceeds to Step 3, where the final structure is generated. The resulting structure can be visualized and downloaded from this screen. Case 2. In Case 2, the workflow is similar to Case 1, but instead of using a predefined linker, the user can provide a custom linker. This can be done by uploading an SDF file, drawing a new structure, or modifying an existing linker from the database. After defining the custom linker, the user follows the same steps as before and verifies the final structure through the structure check process before generating the output. Case 3. In Case 3, Component 2 can also be defined using a PDB Reader project. This is particularly useful for generating antibody-RNA conjugates. In this case, the RNA structure is first prepared using PDB Reader. Then, in the Component 2 section, the user selects the PDB Reader project as the source. If needed, the original coordinates from the PDB Reader project can be preserved by enabling the corresponding option. Please note that when this option is selected, the number of residues selected for Component 1 should match that of Component 2. Internally, the system calculates the pairwise distance between each Component 1 and each Component 2 and determines the pair of components to conjugate while preserving coordinates. The user then defines the conjugation site on Component 2, selects the linker, and completes the conjugation setup as in the previous cases. Structure check. Finally, during the structure check step, special handling is applied if the original structure contains disulfide bonds. If conjugation is applied to a cysteine residue involved in a disulfide bond, the bond is automatically broken to prevent structural instability. However, because the system attempts to preserve the original coordinates as much as possible, minor steric clashes may still be observed. Overall, Bioconjugate Modeler provides a flexible and efficient workflow for constructing complex bioconjugates, including ADCs and ARC, with support for both predefined and custom components.